right, let's look at some practice problems. Here we have this matrix, and we can go through and show that this matrix has two eigenvalues associated with it. Eigenvalue at lambda is equal to -1, eigenvalue at lambda plus 2, and associated with them we have a projection matrix. Each of these we have a projection matrix, a nilpotent matrix. Okay, so how does this work? How do we go about finding these projection and nilpotent matrices? So we start with the characteristic polynomial, Si minus a determinant. In this case, factors this way. So we have repeated poles, repeated eigenvalues for both eigenvalues. This one's repeated twice, this one's repeated 3 times. If we go through and do a partial fraction expansion on this, the full partial fraction expansion looks like this. So notice we have a term s plus 1 quantity squared, s minus 2 quantity squared, s minus 3 quantity squared, and then the associated coefficients. Okay, I can put this over a common denominator, I get this. I can put these guys over a common denominator, I get this. And so this then is x1 of s, this one is x2 of s, and so we have the expression this way. Now I can use this expression to form the EIs. In this case I have 2 matrices, just 2 polynomials. So this is x1 and this is p1. Okay, notice that p1 is the characteristic polynomial without this term. p2 is the characteristic polynomial without this term. Okay, and so this was x2. Okay, so from these numerators. So when I evaluate this polynomial at the matrix A, I get this matrix. When I evaluate this polynomial at the matrix A, I get this polynomial. So notice when I do that, I can basically take s squared, so I replace s by the identity by power of a squared minus 6a plus 11i. Remember, a to the power 0 is the identity matrix. That quantity times a plus the identity, 1 times the identity matrix, squared, and multiply all that together, and that gives me this matrix. Okay, so we've done this for both of these guys, and so this is fairly straightforward to do in MATLAB. Okay, so question is, are these projections? Well, you can go through and show if you multiply this matrix by itself, you get the matrix back. Notice it's not a projector, it's just a projection. Okay, in general we will not get projectors, we will get projection, unless A happens to be a special form like a symmetric matrix. Okay, so you could just try it and plug in the numbers and multiply it out, and you can see it would be a projection matrix. For the nilpotent matrices, I form this quantity. I take the e's, the e, multiply a minus lambda 1 times I, and I would get this matrix. And 2, I get this matrix. And again, you can take this matrix, multiply by itself, and you would get, in this case, 0. If I took this matrix and multiplied by itself, I would get something not 0. But if I multiplied it by itself twice, so n2 to the power 3, I would get 0. Okay, so you can go through and show that. You can also show all of these properties associated with the matrix, that each of the e's are projections, that the 2 e's add up to the identity matrix. Wow. Let's take a look at those. So for example, if I look at the first terms, 13/9 minus 4/9 is 9/9, which is 1. 1, 0. So notice 0, 0, 0, 0. 8/9 minus 8/9, minus 4 nines, 4 9. So you can see everything they just add up perfectly to be the identity matrix. You can go through and show that if you multiply the two e's by each other, you'll get 0. You can show that the e's commute with a. You can go through and show that a can be written this way, that the nilpotent matrices also satisfy these properties. So these e's and n's are obviously very have a lot of properties associated with them, and that makes this a very rich expansion. So again, the characteristic polynomial is given by this. And now we're going to be looking at trying to use the Cayley-Hamilton theorem in interpolation. Okay? So for any analytic function, f of x, we have f of a can be written as this expansion. Okay? No, we're not going to use Cayley-Hamilton. We're going to go ahead and use the spectral mapping theorem. So, excuse me. So the spectral mapping theorem, this is what it looks like for this matrix. It simplifies down to this summation because we only have two eigenvalues to work with. So you have f evaluated at the first eigenvalue times e1. Then we have f, the derivative of f with respect to x, evaluated at minus 1 times the nilpotent matrix. For the second case, we have f evaluated at 2 times e2, f prime at 2 evaluated the nilpotent matrix 2, and then 1 over 2 factorial f double prime at 2 times n2 squared. So notice that if the reason this summation stops again is because n1 squared is going to be 0, and n2 cubed is going to be 0, and so that's why the summation stops here. So we merely need to compute the function and derivatives at the eigenvalues to fill in the blanks here. So suppose we wanted to compute a to the k. Our function f of x then is x to the power k. F prime of x is equal to k, x to the power k minus 1. F double prime of x is k times k minus 1 times x to the power k minus 2. And so a to the power k in this case is equal to f of a, but f of a is this function, and so that's what we're looking for. And so here's the expansion of that. F at minus 1 times e1, f prime of minus 1 times n1, f of 2 times e2, f prime of 2 at times n2, 1/2 f double prime of 2 times n2 squared. So here is f of minus 1. Okay, if I plug minus 1 in for x, minus 1 to the k, e1, plus k, minus 1 to the k, minus 1 to the k minus 1, times n1. And then for 2, we have f of 2 is 2 to the power k. F prime of 2 is k 2 to the power of k minus 1. F double prime of 2 is 2. So this is f double prime, but I have 1 over 2 factorial times that. So I have 1/2 k times k minus 1 times 2 to the power of k minus 2 times n2 squared. So this then is the expansion for a to the power k. And when we, so here's minus 1 to the power k. This, so notice I have minus 1 to the power k, which I can factor out and get e1 plus k times n1. Over here, I have 2 to the power of k's, which I can factor out. And so this is what I get. This is the expression that I get when I do all that. And when I add it all together. So if I add it all together, I will get a mess. I mean, a big hairy mess, but this is what I would get. Okay, so that is the computing of the function of a pretty big matrix function computing a to the power k. So given now that we have the same characteristic polynomial continuing the example now, suppose we wanted to compute e to the at for this function. In this case, f of x is equal to e to the xt. The first derivative is t e to the xt. Second derivative is t squared e to the xt. And so this is the expansion for e to the at in terms of the e's and the n's. Okay, so anyway, this is the expansion. And I could go ahead and plug in the e's and the n's and combine all this together. And that would give it to us. Here's a second example. Suppose we have this problem. So instead of having 1 and 2, I have 3 and 7. Okay, just to give us different numbers to work with. Okay, so if we're wanting to, so for this polynomial, once we've computed the e's and the n's, I can simply write down the expansion for a to the power k, or the expansion for e to the at. So once I've got the e's and the n's, I can compute any function in a fairly straightforward manner, given those e's and n's. So we have a powerful tool to work with. Okay, here's a matrix now. Again, repeated eigenvalues at 2, at -2, and 1 at simple 1 at 1. And so when we do the partial fraction expansion, this is what we get. This is our x1, this is our x2. So e1 is equal to x1 times this. e2 is equal to this times that. Okay, so we have our e polynomials. We can evaluate e to get e1, which is given by this expression. It simplifies down to this. Our n1 is given by this expression. And incidentally, I can go through and show that this is in fact a projection. I go ahead and multiply this out and I get this matrix. I can show that this is a nilpotent matrix. e2 I can go through and compute. In this case, I get this expression. And this is so this is e2, and I get this quantity. I can show that this is itself a projection, and there's no nilpotent matrix in this case because it was a simple pole. So if you have a simple pole, you only get an e, you don't get an n. That's one of the things that makes it simple. So here's this matrix, which we can go through and show has this expansion. So here's lambda 1 e1 plus n1 plus lambda 2 e2. And now we can compute this function of a using the e's and the n. So this is actually, I can look at that as the n. And so e to the at I can write down as this in this form. And when I multiply it out, so when I multiply this out, I get this matrix. So actually this is the nilpotent matrix. I've already computed that. Here's the e1, here's the e2. When I simplify it, I get this expression. And so again, we can easily compute other functions of a. For example, if I wanted to compute cosine of at, this is what it would look like. So this is cosine. For the repeated root, this is the derivative of cosine with respect to t, or actually with respect to 2, with respect to the eigenvalue. So this is f prime evaluated at 2, and then here's cosine at -1, and I would get this expansion for cosine of at. So the spectral mapping theorem is very powerful in that once you found the e's and the n's, we can compute many different functions of that matrix. If you need to. I mean, maybe you don't need to, in which case it may be a little more work than some of the other methods. So in this particular case, this A matrix now can be put into diagonal form. So this is the diagonal matrix. This is the eigenvector matrix. Here's the eigenvector matrix inverse. Okay, so those are the eigenvalues. And so we can easily compute the functions of this. let's look at the Cayley-Hamilton theorem. I have 3 eigenvalues. So if we're trying to compute lambda to the a to the k, so in this case we have lambda to the k must be given by this expression. So so x, we plug in lambdas. Okay, and so we have G0, G1, and G2. I don't know what these are. They're functions of k. I don't know what functions they are of k yet, but I'll find that out soon enough. Okay, so 1 to the power k is given by this. So I have 1's here. 1/2 to the power k, so notice I have 1/2 in here. So this is basically the same equation. It's just that this is using lambda is equal to 1. This is lambda is equal to 1/2. This is lambda is equal to 2 to the k. And so I get these 3 equations, and I have 3 unknowns. The unknowns are the functions g0, g1, and g2. Okay, so I can put them all into a matrix equation. So on this side, I stack these into a vector. I put this into a matrix equation, factor out the g's, and this is what it looks like. Okay. This matrix has a special form. It's called a Vandermonde Matrix. So now I don't know the g's, but I do know this quantity and I know this quantity, and so I can solve for the g's this way. And so this gives me the g's in terms of k, and you can see it is indeed a function of k. And so fa of k then can be written now in this form. Okay, now that I know what the g's are, I can just plug it in here, and away we go, and we get the function a to the k. Okay, given this matrix now, notice that the eigenvalue is repeated, and so if we want to compute e to the at, then f evaluated at -2t is e to the -2t, which must be equal to g to the -2 comma t. And so notice that I'm evaluating this side with the eigenvalues -2, okay, and then I do f prime. So the derivative of f, so f of x is equal to e to the x. So f prime of x is equal to x e to the x. E to the xt. So when I do derivative with respect to x, I get t e to the xt. And so that's where this comes from. So the first derivative is this, evaluated at lambda is equal to -2, must be equal to g prime. So this is g, and I'm going to evaluate it at lambda -2 and t. And so if I take the derivative of the g function with respect to x, I get this expression, and I evaluate it at lambda is equal to -2. And similarly with the second derivative. So I just follow the definition for these g's, and I get these 3 equations. Okay, I can stack these 3 equations into a matrix equation. So these guys would get stacked together on the left, and this stuff would get stacked together on the right. So notice I have G2, G1, and G0 are the unknowns over here, and when I stack them together, this is what I get, and I factor out the g's. This is known, these are known, I can solve for the g's, which are unknown, and this is what I get. And so I get these functions g that are functions of t. Okay, and so when I go through and compute e to the at, g2, g1, and g0, this is what f of 8 and t is going to look like. So these two are equal to each other. This function I have determined, it's this. Here's a squared. g1 I've computed, it's this times a. g0, which is this, times the identity matrix. And I sum it all together. And when I do, I get this matrix. Now whenever you compute e to the at, you can always check to see if you've done it right, if you evaluate at the value of t equals 0. At t equals 0, I should get the identity matrix. So as complicated as this thing looks, if I evaluate this thing to check it, if I evaluate it at t equals 0, notice that when t equals 0, this term goes away, this term goes away, this term goes away, and e's along the diagonal at t equals 0 gives just 1. So we get the identity matrix. So that's a simple check, and that's true for any method that you use to compute e to the at. Also, a to the k, you can also check that. If you check when k is equal to 0, you should get the identity matrix. So in this case, when we were looking at this, when we came up with this equation, and we have this matrix that we were inverting. This matrix, when you have repeated eigenvalues, gives you something called a generalized Vandermonde matrix. Okay, so the Vandermonde matrix itself has a particular form, but this is a generalized Vandermonde matrix. So we've gone through now and shown how to solve these functions of a square matrix and look at several examples. I hope these examples are helpful to you. Thanks for watching.